Hi everyone, welcome back. We are pleased to have Boedihardjo from UCLA, and he's speaking on spectral norms of Gaussian matrices with correlated entries. March?
Okay, thank you very much for the invitation. Um, so, so today I'm going to talk about, if you have a Gaussian matrix, so a matrix where the entries are jointly Gaussian, mean zero, then what would be the norm? So in general, by jointly Gaussian, I mean they're just Gaussian, but not necessarily independent entries. Let's look at one of the simplest case when all the entries are IID rather than jointly Gaussian in general. So in that case, this is a classical fact, the spectral norm. So that means this supremum. The expected spectral norm is of magnitude root D. D is just the size of the matrix. Okay. This is actually another example, but it's somewhat opposite of the previous example. It's still jointly Gaussian, the entries, but then it's concentrated on the diagonal. So the off-diagonal entries are said to be zero, and then just diagonals are ID Gaussian. So in this case, well, the spectral norm is just the supremum, the maximum of all the absolute value of the diagonal. Well, that's of magnitude square root log D. So there is a log D factor that arises if it is diagonal. But then if all the D square entries are ID Gaussian, then we don't have the log D factor. Okay. All right, so let's do the most general case. When all the entries are jointly Gaussian, so assume it's centered, jointly Gaussian, so they could have some correlation between the entries rather than just IID. So with some correlations, well, the lower bound is easy to get. So first, we can use Kahan-Kinchen or concentration. We can see that these two are of the same magnitude. And then this one is greater than this. Well, the square of the spectral norm, you can write that as norm of the x star x or norm of x star, and then you just put the expected inside, and then you just get this. So this is the easier. The lower estimate is easier. The upper estimate is the non-commutative Kinchen. So it's the same as the lower estimate, but then there is a square root log D there. So yeah, so up to the square root log D, the non-commutative Kinchen inequality gives the estimate for the expected spectral norm of such a matrix. Okay, such a matrix. Okay. So when is this equal to this? When is the upper bound sharp and when is the lower bound sharp? Well, the upper bound will be sharp for diagonal Gaussian, the one where all the diagonal entries are ID and the rest are zero, the off diagonal are zero. The lower bound is sharp for the case when all the D square entries are standard Gaussian. So I should also say ID standard Gaussian. So it's not needed. So the lower bound is sharp for the case when all the D square entries are ID Gaussian. Okay. So just restate the non-commutative Kinchen inequality. So what I'm interested in is when can we remove this square log D factor? Okay. If we can remove this square log D factor, then the expected spectral norm, we get a sharp estimate. Okay, so it's up to a constant equivalent to this quantity. So if we can remove this, then the upper bound and lower bound, they match up to a constant. Okay. So that's non-asymptotically. Non-asymptotically, this gives a dimension-free estimate if we can remove this factor. Asymptotically, well, if we look at the spectral distribution, then in the limit spectral distribution, it's going to have compact support like the weakness semicircle law, whereas for Gaussian random variable, the diagonal Gaussian, the limit spectral distribution is the normal distribution, which has infinite support. So if we can remove the square log D factor, then in particular, asymptotically, the bulk would be will have compact support. Not only the bulk, the edge will also be finite. Okay, but of course, this cannot always be removed because, for instance, the diagonal Gaussian, the square log D factor is sharp, so we cannot remove that. So when can we remove? So let's look at some examples. So this is one that I mentioned before, when all the D square entries are ID. For that one, we can remove the square log D factor, and then we get a sharp estimate for the expected spectral norm of X. Or more generally, if we allow actually most of the entries to be zero, so sparse Gaussian, so most of the entries are zero, but then some of the entries we allow that to be ID Gaussian on these assignated entries. They are ID Gaussian. So if it is not too sparse, then we can also remove the square log D factor. And even more general cases when all the entries are independent, but not necessarily the same variance. So why do I need not too sparse? Because if it's too sparse, then the diagonal Gaussian is an example of sparse Gaussian. So that would be too sparse. So diagonal will have D number of non-zero entries. Here, if we have D log D number of non-zero entries, then the square log D factor can be removed. So these are examples where the square log D factor is sharp, so in particular cannot be removed from the non-commutative Kinch inequality, the upper bound. Circulant matrix, where so a circulant matrix can be fully determined using one of the row or column. So let's say we just set one of the row or column to be IID Gaussian, and then the rest of the entries will be determined for circulant Gaussian. So that's going to be a normal matrix, although it's random matrix, but it's normal matrix. So the spectral norm is not too hard to compute because it's normal. For Topliss Gaussian, so let's say the first row and the first column, they are IID Gaussian entries, and then the rest will be determined. In that case, also the square log D factor is needed. Okay, so yeah, so this is what's known in the literature. Probably there's still more examples than these, but most of what is known in the literature is limited to examples. So in each example, we know whether the square log D factor is needed, but in the most general setting, little is known about when the square log D factor can be removed. So there's a notable result of Trop. So he studied in this direction of when the square log D factor can be removed. So what he did was he reduced the square root log D factor to log D to the power 1/4 with this trade-off. Of course, we need to have a trade-off, otherwise with the diagonal Gaussian, it won't be true. Well, the trade-off is this thing. So the assumption is that X has jointly Gaussian entries. So we can write X as sum of GK times AK, and the AK are deterministic matrices, and then WX is just this thing. So there could be multiple ways to write X in this form, but this quantity won't depend on the specific choice of the AK. If we write in another way in this form, this WX will give the same value. So this result is obviously not too satisfactory. First, there's still the log D to the power 1/4, still not yet dimension free. So it still involves a dimension in the estimate. The second issue is that this one is very hard to compute in general because we have to take supremum over all the unitary Q1, Q2, Q3 inserted in between. So what Trop did was he computed this for Wigner matrices, but then just for Wigner matrices, but then beyond Wigner matrices, and almost all the time it's very hard to compute this quantity. Even for Wigner matrices, it takes quite some computation to calculate this thing, even for Wigner matrices. For general matrices, this is very hard to compute. All right. But despite these issues, this result points us to the right direction to getting the main result of what we get. Okay, before I present the main result, I just want to restrict to this special case. And then in this special case, it's easier to see what our main results mean in this special case. So this is standard Gaussian on an inner product space. So take any orthonormal basis for a given inner product space M, and then take IID standard Gaussian. So sum them up, this linear combination of this AK of this orthonormal basis with coefficient being the ID standard Gaussian. So this becomes a random variable on this inner product space M. So the distribution of this random variable will not depend on the specific choice of the orthonormal basis A1 to A of dimension of M. If you choose another orthonormal basis, it's going to give you the same distribution. So an example would be take a subspace of the space of D by D matrices, and then the inner product is just given by this thing. Inner product of A and B is trace of A and B transpose. Okay, so with this inner product, we can define a standard Gaussian on a given subspace of the space of D by D matrices. Okay. So this is a random matrix because M is a space of D by D matrices. So if we take a standard Gaussian on M, that's going to be a random matrix. Okay. And actually quite a number of random matrix models are actually of this form. So first, if all the d-square entries are ID standard Gaussian, then this is the standard Gaussian on the space of all d by d matrices. Diagonal Gaussian is the standard Gaussian on the space of diagonal matrices as a vector space. Band Gaussian, so that's the matrix where those entries near the diagonal, they are ID Gaussian, but then entries that are far away from the diagonal, then they're set to be 0. So it's a generalization of diagonal Gaussian. Just that we relax, rather than diagonal, we allow those entries near the diagonal to be ID Gaussian also. But if it's far away from the diagonal, then it's 0. That's band, random band matrix. Sparse is even more general than the band. So most of the entries are 0, but some of the entries, we allow them to be ID Gaussian. And then circulants and topless, I think I talked about that. There's a generalization of these two actually, glued entries. So that's, okay, so what is circulant Gaussian? So it's like this one, but then the thing is we force a lot of entries to be the same. Topless also, we force all the entries in the same diagonal to be the same. So just force some of the entries to be the same, and then beyond what we force them to be the same, they are ID Gaussian. So I think I will talk about this later. So this is generalization of these two, because in both circulant and topless, we just force a lot of entries to be the same. Okay, so these are all examples of standard Gaussian on a subspace. So circulant Gaussian, that's the standard Gaussian on the space of all circular matrices. This is the standard Gaussian on the space of all topless matrices. Okay, so this result will follow from the main result that we get. So in the Khinchin and the non-commutative Khinchin inequality, what's the sharp constant that depends on the dimension that satisfies this? I think I typed this wrong. It's less than equal to. It's not equivalent. It's less than equal to this one. Okay. So the expected spectral norm of a standard Gaussian on a subspace, let's say that subspace has dimension d power alpha. Well, a subspace of the space of d by d matrices is going to have dimension between 0 and d squared. So alpha is going to be between 0 and 2. Okay. Assume this is a non-zero subspace. Alpha is going to be between 0 and 2. And then I should put inequality rather than equality of the constant. So what is the sharp constant in the non-commutative Khinchin inequality for standard Gaussian on a subspace? It's given by this. So if alpha is between 0 and 1, we do need a square log d factor, because we can take a space of diagonal, the subspace to be a space of diagonal matrices. Then in that case, we need to have square log d to the power alpha, and the square log d power alpha is equivalent to square log d. But then if alpha is bigger than 1, we can completely remove the square log d up to a dimension-free constant that depends on alpha. That's if alpha is strictly bigger than 1. Okay, so yeah, so there's some kind of a jump. Before 1, it is necessary to have a square log d factor. After 1, then we can completely remove the square log d factor, and then it's a dimension-free estimate. Okay, so is there some intuition from the Banach space point of view? I don't see the intuition, but from the operator algebra point of view, this is the intuition that we have. Let's say this is a self-adjoint subspace, so all the, this is a real subspace. So let's say all the matrices in that subspace are self-adjoint. Okay. Then if alpha is less than or equal to 1, so if the dimension is less than or equal to d, if the dimension is less than or equal to d, it's possible that this is a commutative subspace. For instance, the space of all diagonal matrices that's commutative. Okay. And then if alpha is bigger than 1, then dimension of M is strictly bigger than D. And if dimension of M is strictly bigger than D, it's impossible that M is going to be commutative, because if M is commutative and if all the matrices in the subspace are self-adjoint, then we can simultaneously diagonalize all the matrices. In other words, up to a change of orthonormal basis, all the matrices in M, they are diagonal matrices. But then for diagonal matrices, that has dimension at most D. So if the dimension of M is more than D, it's impossible that it's going to be commutative. And as alpha, which controls the dimension, as alpha gets larger and larger, the dimension gets larger and larger, then it's more and more away from the commutative case. And if it is more away from the commutative case, then the opposite extreme of commutative is freeness. And then if freeness arises, then somehow we get a dimension-free estimate, because in free probability, the free central limit theorem gives the semicircle law, and then for semicircle law, that has compact supports, whereas for the classical Gaussian, from the classical central limit theorem, that has infinite support, and that's why we have the square log D, because that's really the LP of a standard Gaussian for P equal to log D. But then for semicircle law, it has compact support, so that's why it's dimension free. So that's it, but this is just intuition. Okay? Why it's dimension free for alpha bigger than 1, and it has to involve some dimension for alpha less than or equal to 1.
But is that the reason you suspected there was a phase transition, this intuition at the bottom?
Yes, we actually had this intuition before we even able to prove this, yes. In terms of the proof, the freeness corresponds to the non-crossing partition in the language of combinatorics. And then the classical commutative case will correspond to all the partitions rather than non-crossing partition. And then for non-crossing partition, it has only exponentially many number of non-crossing partition on a set of size P, but for all the partitions, it's super exponential. This is from the proof, we just explored the fact that non-crossing partition is only exponential growth, the size of non-crossing partition. And then we show that the crossing partition will be small. We show that crossing partitions are small, and then non-crossing partition, they're only exponentially many. And then once we take 1 over P on both sides, we just get a dimension-free estimate. Okay, and let's go back to some of the example, the standard Gaussian on a subspace examples we did. If all the d-square entries are ID, that's the standard Gaussian on the space of all the d by d matrices. So that subspace, well, there's really the whole space that has dimension d squared. For sparse Gaussian, where some designated entries, they are IID Gaussian, elsewhere is 0, while the dimension is just number of entries, we allow them to be IID Gaussian. And our result is consistent with what is known about sparse Gaussian. Well, diagonal Gaussian, that's subspace has dimension d, circulant also dimension d, and Toeplitz dimension something like maybe 2d minus 1. Okay, so these are for alpha less than equal to 1. All of these are alpha less than equal to 1. This one is alpha bigger than 1. And as for sparse Gaussian, well, it depends on the number of non-zero entries. But what we prove is consistent with what is known. Okay, there's also the glued entries, which I mentioned before. This is a generalization of the circulant and the Toeplitz matrices, where we force a lot of entries to be the same. So in other words, let's set a partition for the this set. Okay, this is the set of all entries of a matrix. Okay, a D by D matrix, the set of all entries. So set a partition for that, the set of all entries, the D square number of entries. So set a partition for that. And then let's say each block in the partition is not too large. Then the random matrix is just that for entries that are in the same block of the partition, they are forced to be the same. And for entries in different blocks of the partition, they are IID Gaussian. So in the same block, they are forced to be the same. And then across different blocks, they are IID Gaussian. So that's the random matrix model. So then our result, actually we do something better, because our result we have just given d power 1 minus epsilon, but here we actually get d over log d power 4. We get an exact estimate for this up to a constant. Okay, and the AK is just the matrix where on the SK is 1, and then elsewhere the entries are 0. Okay. But anyway, we do get an exact estimate for the expected spectral norm if the blocks of the partition is not too large. But then if each block, is, let's say this one, okay? So rather than less than equal to d over log d power 4 is equal to d, then this result will fail, because random circulant is an example where we force d number of entries to be the same. Each block is of size d. We force all the entries in the same block to be the same. And then for random circulants, we have a square root log d. So this result would fail for random circulant. So if we just relax this to equal to d, this already fails. Okay, the main result is this. The non-commutative Kinshasa inequality is square log d times this whole thing. But then what we do is we eliminate the square log d, and then we add this thing. What is this thing? So this is a linear transformation on this inner product space. Okay. This is the inner product space of all d by d real matrices. And then it's inner product space because we can take the inner product to be inner product of A and B is just trace of A times B transpose. So this is a linear transformation on this inner product space. And being a linear transformation, it makes sense to consider the spectral norm of this linear transformation. Okay. And then if this thing dominates this, then we get an exact estimate up to a constant that depends on epsilon for the expected spectral norm. Okay, let's see, how much time do I have?
20 minutes.
So let's do more examples. So standard Gaussian was one example of the main result. Here's another example. So let's say we take a rectangular matrix, and then all the rows are independent, but not necessarily IID rows. Just independent rows, not necessarily IID rows. And then the ith row is a centered Gaussian. Okay. And then the covariance matrix for that centered Gaussian for the ith row is given by a positive semi-definite matrix BI. Okay. And then all the BI are different. Okay, for different I, all the BI are different. So it's only independent rows, but not necessarily IID rows, because for different rows, the covariance matrix of that row is a different matrix. Okay, it could be very different matrix across different rows. So this B1 to B of D1, they could be very different across different rows. If we assume that each BI is not too spiky, so the largest, so this is the largest eigenvalue. So let's say that at least this number of eigenvalues that are of the same magnitude, of the same order as the largest eigenvalue. The trace is at least this one. So let's say, so it's not too spiky. So rank 1 would not satisfy this, but so this is somewhat like the stable rank or effective rank. Okay, the effective rank is at least this. Okay, so this is not too strong condition because this is not, it's not close to D1 or D2. This is still much less than D1 or D2. So roughly speaking, a stable rank or effective rank, okay, is greater than or equal to this quantity. Then we get an exact estimate for the expected spectral norm up to a constant depending on epsilon. So that's the formula. But if we remove this assumption, then this would fail because diagonal Gaussian is an obstruction. Diagonal Gaussian, it has independent rows. Of course, the covariance matrix of each row are very different. And for each row, the covariance matrix would be of rank 1, and it won't satisfy this. Okay, so assume the covariance matrix is thick enough, okay, rather than rank 1, then it will satisfy this. We get a up to constant exact estimate. So this assumption is needed. So from the one we have for independent rows, we get an estimate for the expected spectral norm of the sample covariance matrix from mixed Gaussian. Okay, so mixed Gaussian, that's a model for random vector. So this is n of 0b is the centered Gaussian with covariance matrix B, and then we just integrate this. So take a mixture of Gaussian, so mixed Gaussian. Now this is centered. Just want to make it simple, make it centered. So yeah, so we just take a probability measure on this and then do the mixture. So if we take IID samples, then, well, this is covariance matrix. If we divide by D1, okay, and then of course from what we had for independent rows, we get an estimate for the expected spectral norm of the covariance, sample covariance matrix. That's this formula. If almost surely it is thick enough. So trace of B is much bigger than the spectral norm of B. So the effective rank of B is not too small, almost surely. If the rank is not too, effective rank is not too small, almost surely, then we get such an estimate. So up to constant, this is equivalent to this. Now, this is only the expected spectral norm of sample covariance, but what about the error between the sample covariance and the covariance matrix? So this is, well, we're going to study. So this is the sample covariance estimation problem. How many samples are needed to get an accurate estimate for the covariance? So how many samples are needed so that the sample covariance matrix is close to the true covariance matrix? Okay. Well, this is this problem has been studied a lot for the isotropic case. If it is isotropic and if the order is of order root D. Now, if it's isotropic, of course, the order is of this, but I mean, not just the expected value of this thing square, but in the strongest sense, this is of order root D. Okay, not just expected value of this square. Then D log D samples, that's enough. If we want to remove the log D, then we need some impose more assumption. Otherwise, there's the coordinate random vector. Then for that one, we do need D log D. So we do need some assumption. So assume that each one-dimensional marginal, it is smooth enough. So isotropic only gives the Q equal to 2. But let's say in each one-dimensional marginal, it's not too bad. Fix the Q bigger than 2. This is bounded. Then D samples is enough. We can remove the log D. Okay. Now these are isotropic cases. For the non-isotropic cases, one of the simplest model is Gaussian, but just that the covariance matrix is not the identity. Then the effective rank of the covariance matrix is what we need. That's the number of samples we need to take. Of course, we have to multiply by constant depending on how accurate we want, but that's the order. So the effective rank is the number of samples needed to get accurate estimation of the true covariance matrix. So that's for the Gaussian, but non-isotropic Gaussian. Okay. All right. So what about mixed Gaussian that I talked about before? Well, mixed Gaussian are actually quite different from Gaussian, actually. Yeah, so mixed Gaussian. So we fix a probability measure on the space of all, on the set of all positive semi-definite matrix, and then pick a mixed Gaussian random vector. So a mixture of these Gaussian distribution. So how many samples are needed? Okay, so it's natural to think that mixed Gaussian is average of Gaussian. So it should not be too much worse than Gaussian. It's natural to think like that. But actually, mixed Gaussian can be very bad. Mixed Gaussian can be very different from Gaussian. So what is known for Gaussian is not so straightforward to imply that, what can be proved for mixed Gaussian, because mixed Gaussian could be very different from Gaussian. So just want to do an illustration why mixed Gaussian are very different from Gaussian. Well, just like for Gaussian, Well, mixed Gaussian can be non-isotropic, just like for Gaussian. But what's so different from Gaussian is that when a Gaussian random vector is isotropic, then it behaves well, because if we look at each one-dimensional marginal, it's going to be a sub-Gaussian. The LP normal of each one-dimensional marginal is going to be good. But on the other hand, even if a mixed Gaussian is isotropic, it can still be very bad if you look at the one-dimensional marginal. So by very non-isotropic, I mean, in some of the one-dimensional marginal, it could be good, but in another one-dimensional marginal, it could have completely different behavior. So yeah, so here's an example where we have isotropic, but then if we look at the one-dimensional marginal, then no, it can be very bad. So the issue is that a lot of the known results about sample covariance estimation for isotropic random vector, lots of known results about isotropic random vectors, the sample covariance estimation, do not apply because this one, the one-dimensional marginal just with Q bigger than 2 can already be very bad. So lots of known results do not apply. Reducing inequality will apply, but then reducing has a log D. Okay, so the example is this. So we pick a decomposition of our D, and let's say D is a square number. We decompose that as the direct sum of root D number of subspaces, and each subspace has dimension root D. Okay, orthogonal decomposition, root D number of subspaces, each subspace has dimension root D. And then we take this mixed Gaussian, so it's going to be, we can consider a standard Gaussian, well, not standard, but a scaled standard Gaussian on each subspace. But then it's randomly the mixture, just take the mixture of this. So it's, it's very spiky actually, because we first pick the one of these at random, one of these root D at random, this root D number of subspaces at random. We first pick one of these root D number of subspaces at random, and then after we pick that subspace, we pick a standard Gaussian on that subspace. So it's very spiky actually, but still we can consider the mixed Gaussian. Okay, and then this is going to be isotropic because if you take the average of these, it's going to be identity, this covariance matrix. But then the one-dimensional marginal, they can be very bad as long as Q is bigger than 2. But still in this case, order the number of samples that's enough. Okay, isotropic. In general, for isotropic, if it's not too bad, then D log D, that's guaranteed to be enough by reducing. But then here, we don't need the log D, despite, it's very bad behavior, the one-dimensional marginal, but still D number of samples, that's enough. Okay. So one might wonder, is it true that for all mixed Gaussian, if it is isotropic, then D number of samples, that's enough? Well, not always. We can take an even worse one. This one is even more spiky. So this is just rank 1, okay? So pick one of the coordinates and then pick a Gaussian on that coordinate, the rest are all 0. That's even more spiky. Then that one is isotropic, but we need the log, I think we need a log D factor. So D number of samples, that's not enough. So this is mixed Gaussian, but even more spiky, but then D samples not enough. So sometimes D samples enough, sometimes D samples, that's not enough, okay? So for mixed Gaussian, it could be very different from Gaussian. For Gaussian, if it is isotropic, then has very good behavior. But for mixed Gaussian, even if it is isotropic, the one-dimensional marginal can be very bad. But even if it is very bad, sometimes D sample is enough, but sometimes D sample is not enough in the case that it is very bad. How much time do I have?
About 4 or 5 minutes.
Okay. All right, so let's go back to the sample covariance problem. So how many samples are needed for the sample covariance matrix of mixed Gaussian to be an accurate estimate of the covariance, the true covariance? Well, here's necessary, so at least this number of samples is going to be needed, because if we take the spectral norm of this one, this is at least the norm of the sum is at least the norm of each of them. And then the norm of any one of them, that's norm of zi square. And then norm of the sum is at least the max of the norm of any of them, okay? So if we condition on the bi, so how are the zi chosen? They are mixed Gaussian, right? They're mixed Gaussian, so we first pick the b at random according to the measure mu. And after we fix the b, we take a Gaussian with respect to the covariance matrix B. So if we condition on the B, and then we put the expected inside the max, that's what we get. Okay. On the other hand, if you look at the spectral norm of this, what's the true covariance matrix? Well, for mixed Gaussian, the true covariance is just the average of these B. Okay. So the norm of this is the norm of this, but then the norm of this is at least this thing. So if M is the number of samples that satisfy this, then M will satisfy this. Okay. Now this is a bit circular because there's M here and M here, but this is a necessary condition. Okay. So if the sample size satisfies this, then the sample size will satisfy this. M has to be at least this number. And roughly speaking, if it is deterministic, if all the BI are the same, then this is the effective rank. Okay, and this is like what we have for the classical case for non-isotropic Gaussian. If all the BI are the same, okay, then this is just the effective rank, trace of B over norm of B. Okay. But this is only necessary, okay, for mixed Gaussian. Okay, so yeah, just want to recall. So this is necessary, but what is sufficient is this. Okay, so rather than dealing with the max of all the trace, let's suppose that all the trace are at most T, rather than dealing with the max of all the trace. Assume all the trace are at most D, as at most T, and then the spectral norm is much less than T. D is the size of the matrix, the dimension. So assume it's thick enough, so the effective rank is not too small. The spectral norm is much less than the trace. Then, roughly speaking, this one is enough, okay? The trace is at most T, so this is like T here, and divided by the norm of this. And this is just constant depending on the accuracy. So roughly speaking, this is already enough. If it is thick enough, the effective rank is not too small. So roughly speaking, this is both necessary and sufficient. Okay, this number of samples is enough. Of course, this assumption cannot be removed. It is too thin, too spiky. Then we do need a log D factor. And this is also a consequence of our main result. Okay, that's the summary. That's the main result, which removes the square log d with this trade-off from the non-commutative Gaussian. As a consequence, for standard Gaussian, again, this is less than equal to, up to a constant less than equal to. For standard Gaussian, we have this sharp constant, okay, up to a dimension-free alpha. And then for mixed Gaussian, the number of samples needed, it is necessary that it satisfies this, but then somehow this is also sufficient if it is thick enough. The effective rank is not too small. Roughly speaking, this is also sufficient. And mixed Gaussian can be very different from Gaussian, because even if it is isotropic, it can have very bad one-dimensional behavior. Okay, there is this conjecture that would improve what we get for our main result. So this conjecture, I just want to make an illustration of what this conjecture means. So there's still an example where it's rather than all the entries are ID Gaussian, it's block matrix, okay? So all the Gij, the ID standard Gaussian, and then multiply by deterministic block, okay? For that one, the main result would give such an estimate, but then we have the maximum overall the Frobenius norm of each block matrix, okay? If it's not block matrix, just a scalar in each of them, that's already known. That's the case when they're independent entries. But then if that conjecture that I showed you in the previous slide is true, then we can replace this Frobenius norm by the spectral norm. And that would be very good because, you know, in general, this one would dominate the norm of this, even with this dr power epsilon. In general, this would dominate this, okay? Well, this is always greater than equal to this. And then even if we put dr power epsilon, in many cases, this will still dominate this. But then what our main result gives is only with the Frobenius norm. So if that conjecture is true, we can remove this Frobenius norm, just become spectral norm. And finally, that conjecture, if it is true, it will imply this conjecture in the Banach space setting. So this Banach space satisfies this. So this is like type 2. So without this thing, it's like type 2. Okay, just this thing, this is type 2. But then for type 2, the constant will be, I think, a square root log d. But then we don't want to put square log d here, so add this one. Now this is smaller than this, so put the square log d on a smaller thing. So would the Banach space of all d by d matrices with the spectral norm satisfy this? Well, for L infinity, the d-dimensional L infinity will satisfy this. In fact, even without this term, L infinity space will satisfy this less than equal to this without this term. Okay, that's it for today.
Okay, thanks so much. Any questions?
Now, March, in your main result, there's a constant depending on epsilon. It would look like probably for applications, if you knew what this, the order of this constant, you might do some of the finer things. Do you have any idea what the order of the constant is?
Oh, it's going to be very bad. Let's say this is d to the power 1 plus epsilon. The constant is e to the power 1 over epsilon.
Oh.
So I want to hide it.
Flo, you have a question?
No, apparently not.
Okay, by accident maybe. Anybody else? Okay, then if not, thanks again, March. Thank you very much for the talk. And
My pleasure.